Hello everyone, welcome back. So in the last class I have told you what is a learning with error problem and what is RLWE, that is ring variant of learning with error problem. Now let us see what is this multi-key FHE. Before going to multi-key FHE, quickly recall what is FHE. See, what is a fully homomorphic encryption? You wanted to compute something on your plain text. Suppose I am having M1 and M2. I would like to compute something. What I do, I'll just convert it with my, I will just encrypt my messages, correct? And then I'll give it to the cloud. I'll give the message, put the encrypted message, and I'll also give the function which I would like to compute. Function I am giving. What cloud should provide me? Cloud should provide me this f of m1 m2, which is again encrypted. Okay, then what I'll decrypt it and get back to my f of m1 m2, which I wanted. This is what your FHE scheme is, or in simply let us see what FHE scheme is. I'll just write everything. Okay, it has only 4 algorithm, or some case it is 5. That is setup, key generation, encryption, decryption. Yeah, first is setup, key generation, encryption, decryption, and evaluation. This is your scheme. Let me write it as, so it is 5 tuple. Let us see one by one what are they. Okay, first is setup. In setup, what happens? You will get the parameter, just include give the security parameter, correct? That means output the public parameter params, let me call it as params, the parameters. If you give the input to the setup that this lambda is security parameter, if you input 1 is to lambda, that means maximum value of the maximum value of bit. If you input, then you will get the parameters. This is the first step setup. Next is key generation. In the case of key generation, what if you input the params, this parameter in the key generation, what you will end up, you will be having your public key and secret key. You will get your public key and secret key. It output public key and secret key. Okay, so this is what your key generation is. In the case of encryption, what happens in the case of encryption? You will be giving encryption, you will be giving your public key and your message. It will encrypt and it will give you a ciphertext C, which is a ciphertext. So that means using your public key, you are going to encrypt your message. Mostly here we are taking bit, that is 0 or 1. Okay, you'll get your ciphertext. Next, decryption. In the case of decryption, you are going to, let me just write, you are going to give your secret key and C. That means by using your secret key, you have to decrypt your ciphertext. You will get back to your plain text message M. Okay, using your secret key. Next thing is evaluation. Evaluation, that means what, you should able to compute any function, any circuit on this scheme. See, in short, if I say that evaluation is a function that makes the encryption scheme special, because for every function f and the ciphertext, suppose I am having so many ciphertext for the different plain text which can be decrypted with the secret key sk, it should provide the that is, if you decrypt the evaluation you should get the result. In short, let me just write it and it will be quite clear. Say for every function, for every f and ciphertext say I am having c1 which is encryption of message m1 with your public key, c2 which is encryption of your m2, and so on. I am having some messages, say cn equal to encryption of some, I am having n messages, I am encrypting it with my public key. These are the ciphertext. Okay, so what is the rule of this eval function? These ciphertext can be decrypted if you apply your secret key as per the decryption protocol. Okay, it should provide the following. It should provide the following. What is that? The new ciphertext is c new, which is equal to eval. The cloud is going to provide us. See, I told you in previous diagram what I am going to do. I am going to give this encryption of the message and my function to the cloud. What cloud should give me? Cloud should give me this guy. Okay, so this is my c new ciphertext. So it is my c new. This is evaluation of your function with the ciphertext, correct? Now if you decrypt this ciphertext, this should imply that if you decrypt this c new with your secret key, then you should get back to your function. This is what I had written, correct? Later on I have to decrypt it. I'll be using my secret key, correct? Here I will be using my public key to encrypt, and then I'll give it to the cloud and cloud will do this decryption. Sometimes we have to have one more key, that is evaluation key, that should also be given to the cloud to evaluate. In some cases this is to happen. We'll be coming to that. And why it is called FHE? Because I am able to do any computation, any type of function, correct? Okay, but for many application it is not necessary to be able to compute an arbitrary number of operation. We just have to do some little bit addition or multiplication or something like that, correct? So in that case, somewhat homomorphic encryption allows computation on limited complexity to be performed, which I had already discussed. And even after that, there is a leveled FHE which can compute on the depth, some depth of your some level will be given, correct? In that case, the size of the public keys depending on the linearity on the number of computation that can be performed. Okay, now let us see what is multi-key FHE. Okay, see, so far we have been looking at the single user setting where all the ciphertext must be encrypted under the same key, and it could be interesting to look at the situation where we don't necessarily need to do the same. Suppose I am having some more person, I am having say p1 p2, say there are two different people, he is having a message m1, he is having a message m2, and they would like to compute this f of m1 and m2, correct? One way is you can do multi-party computation, correct? If the function is small, if that is, if you are just want to calculate average of this or some maybe multiplication or something like that, if the function is small, then you can use multi-party computation, correct? But if the function, if I am having this circuit which is very large, which the parties cannot do, they are not yeah, they are actually inefficient to do the computation of this. So what they are going to do, they are going to use this multi-key FHE, where they are going to first encrypt their messages, correct, with their public key. So both of them having, he is having his public key or his secret key. See, a common public key, that also okay. Or he's having one public key and he is also having his public key, correct. And then they are, what they are doing, he's encrypting it with his public key. This guy is encrypting with his public key, correct. Or public key can be same also. And see, it can happen that there is one public key and corresponding there are two secret keys. That means you cannot decrypt by only, if you encrypt a message by this public key, you require both of them to decrypt it, correct. So this is something like encryption is okay, encryption can be done with this public key, but for the decryption I need all the secret keys. So it is not like the traditional encryption scheme where you are having a public key and a secret key, where if you are having a message, you encrypt it with your public key, you will get your message encrypted, and to decrypt you will just use this secret key and you will get back your message. But here in this case, what is happening, I am having this public key and I am having two secret keys, say sk1 sk2, these are the secret key. So I can encrypt my message with my public key, that can be done. But to decrypt, I won't able to decrypt with one secret key, this won't be possible. Or I won't able to decrypt with second key, secret key only, it won't be possible. So what I can do, I have to use both the secret key sk1 and sk2, then only I can get back my message. It is something like this. It is something that if you relate it with secret sharing, it could be quite similar to that. In secret sharing also, I am having one secret, the shares used to be allotted, say s1 s2 s3 s4. So if all the people combine, then only they can get back to the shares. So it is something related to that. Okay, yes, so now we have understood what is the main motto of this public key multi-key FHE scheme. Okay, yeah. So what happens, I'm having my public key, secret key, either this public key can be same or different, so we'll be mentioning that. What they are doing, they are encrypting their message and then they are giving it to the cloud, correct. And they have to give the function also, which function they would like to compute, correct. And the cloud will give this f of m1 m2, which is encrypted, correct. And to decrypt it, both the person have to involve, as I told you, they cannot decrypt it with only one secret key, so both the secret key need to be involved, and they can get this f of m1 m2, which is easy, which can be done with multi-party, because here there is not much computation that can be easily done. So this is what the basic multi-key FHE scheme, this is how it works. Okay, yeah, let us now see the definition. So as told in the previous class, this multi-key FHE was introduced by LTV12 in 2012, that is Lopez, Tromer and Vakunthanathan. Okay, so what they have given the multi-key FHEs, this was the definition they had given, and they had given a multi-key FHE based NTRU, MKFHE based NTRU, which we will be doing in the next class. But now they have given one more beautiful property, that any FHE scheme can be converted into multi-key FHE scheme. Any FHE scheme, this is what they have said, which was very fabulous, that any FHE scheme is multi-key. Any FHE scheme is multi-key. Multi-key FHE, multi-key for constant number of keys. For constant number of keys. Which was very fabulous result. Let us try to see what they want to say, that if you are having a FHE scheme and you are having constant number of keys, that means you are having constant number of participants, then you can convert your FHE into multi-key FHE. Let us see. So they have used the idea of onion encryption decryption. Onion encryption and decryption. So suppose I am having n parties. I am having n people, each having their messages, each having their public key and secret key. So he is having PK1, SK1, he is having public key 2, secret key 2, and so on. SKN. Okay. So each of them, this is the key they are having, these are the parties. Okay, I'm having n parties. So what happens? Suppose I message M. Suppose a message M, which is say 0, 1, which is a bit. This is the message. First, what you have to do, you have to encrypt the message with their public key, and then that should be converted. See, as I told you, what happens in multi-key FHE, if I'm having somebody, so first message used to be encrypted, and then you have to encrypt it with the common public key. Correct? What happens in this case? See, suppose first party is having message M1. Okay, he encrypt with his public key PK1. Then the second party is going to encrypt the whole thing, M1 PK1. This cipher text he is going to encrypt it with his public key. And the next party, this is P2, next party, he is going to encrypt this thing with his public key. So M1 is going to encrypted with public key 1, and it is again encrypted with public key 2, and now third party, what he will encrypt this. So that's why it is called onion encryption. And at the case of decryption, first third party is going to decrypt, then this circle will break, then the second party, then this will be break, and then second, it is like you are having this chakra view, and you have to reach this message, you have to decrypt with first with the third guy, then second person should decrypt, then first person should get something like that. That's why it is called onion encryption decryption. Okay. So what happens in onion encryption decryption, where the cipher text are repeatedly encrypted or decrypted with a sequence of keys. As I told you, the first message is a message has to be encrypted with a sequence of keys. First with the first person, then the next person. Then so here the sequence is very important here in this encryption. In this case. Now, if you want to see here, what happens? First, my message was there, and I encrypt the message. Now, this guy, this encrypted is not a 0 1. This is not having 0 1 element. This is not a bit. It may have some length, say L. Correct. Then to encrypt this, just have to define what is the encryption of this guy. Correct. So what happens actually? You have to encrypt each of them. So let me just write it. So if we want to encrypt a ciphertext again under a different key, we need the definition for encrypting the element x, which is say L bit, correct? So that means this x can be written as say x1, x2 up to xl. Okay, so how do you define the encryption of this guy? So encryption of this is defined like this: with the public key x, it is equal to encryption of each of the bit with the public key. That means encryption of public key of with the public key I'm encrypting x1, with the same public key I'm encrypting x2, and so on. This is what the meaning of encrypting this vector x and ll. This is L bit. Okay, so this is my new encryption, correct? Now what is the onion encryption? So let me just define onion encryption. I'm going to represent it as encryption star. Okay, for any key belongs to natural number. Any key belongs to there are n parties, so I'm taking any party and I'm just trying to see what happens. Okay, if you are having one public key, sorry, one ciphertext, that is encryption star. If there is only one public key, then it is same as your this guy, encryption of pkx, which I told you, which pkm, which was this, that is encrypting each of the coordinate. Now if I'm having two public key, then what happens? If I'm having three public key, then what happens? So in the case of say I am having k public keys, pk1, pkk. Yeah, I'm talking about kth party. And the message. So what happens in this case? In this case, this encryption star first goes with the kth party, as I told you. So he is going to encrypt this with his public key. That means the first party is going to encrypt, and then this encrypted thing will go to the second party, and that will be encrypted again with the public key. Okay, so first what happens, this by using this kth party's public key, it was encrypted. Now this is my new ciphertext. I have to encrypt with pk minus 1. Do you see, every time I have to do the same thing? So it is something like, let me just write, it will be encryption of, with the public key, the ciphertext of encryption of, with the public key 2, and so on. At last it will be encryption of with pk, public key k of the message. Correct? This is what the meaning of onion encryption. And for decryption, what happens? Decryption, first you have to break this guy. To break this chakravyuh, you just have to use the secret key 1. Then only you can break this chakravyuh. This will be broke. Then in the next case, this is encrypted by public key 2. Then you have to use the second secret key. Then this will break. Correct? And at last you have to use public key, secret key k. Then this will break. You will get back your message. This is what your onion encryption and decryption technique is. Okay. And what do you see? The ciphertext here. Note that. Put a note. Note that a ciphertext produced by encryption star, that is onion encryption, encrypting a message under n keys, has the size lambda raised to n. Okay, in the similar case you can write the decryption. If you see the decryption star is defined as decryption of, if you are having only one secret key, if you are having many, decryption star of sk1, sk key and c, then what is the ciphertext is going to be, this is actually decryption star of first, it will be decrypted with, see in this case I should write here from k to 1, because this ciphertext first it will be decrypted with the secret key 1, so it will be secret key will be as it is here, and here I'll be having secret key 2, and then decryption of with secret key 1 your ciphertext. First it will be decrypted, then first bracket will get out, I'll be remaining with the second one and so on. Correct, so I can write it as, this is same as decryption of with secret key k, decryption of and so on, it will be decryption of sk1 and c. This is what your decryption is. So what is happening actually, do you see a ciphertext ci, let me write, if you are having a ciphertext ci, encrypting message mi with public key pi, can be turned into a new ciphertext, can be turned into, that means it is ciphertext expansion is happening, new ciphertext CZI, that is encrypting the same message, that is encrypting the same message but under key public key, under pk1 pk2 up to pkk, it is something like that. See here, order is also important in this case, you have to make sure that order should not break. See, when the ciphertext involved have been changed into ciphertext encrypting the same message under all the keys, it is possible to perform homomorphic operation on them. Now, once it is once this new encrypted ZI, it is encrypted by all the public key, then for every message we can do the same thing. Then we can we can homomorphically evaluate any circuit actually. You can homomorphic operation can be done keeping in mind the order of the keys involved. That's what I told you. See, if there are 10 parties, then every party should decide that first party will first we have to encrypt it with the first party, then second party. It should not that third party is encrypting first with his public key and then he is using first party's public key. That is not the case it should be. And the case is actually size of this zi is your lambda raised to n, where n is number of keys. Size of ciphertext zi is lambda raised to n, where n is number of keys. Correct? And this can only be efficient if n is constant. This is efficient only if n is big of 1. That is, if I'm having constant number of people, then this is okay, then this can be done. In other word, only a constant number of keys can be involved, correct, to do this. Okay then. See, later on we can even do some more improvement in this, right? But this is not efficient way to go to home or go to multi-key FHE. See what was our aim? We said that in the LTV to 2012, that is the paper by Lopo, Stromer and Vacunar, they said that any FHE scheme is multi-key FHE for constant number of keys. But do you see the ciphertext expansion? It is very large now, because every time you are encrypting the ciphertext, the size is changing and it is very large. So if you are having 2, 10 or 100 parties, 100 number of member, then it is quite difficult. But if you are having less than say 25, then you can do. So accordingly, so this is not a efficient way to convert FHE into multi-key FHE. So thank you so much.